Welcome back to a new lecture. Today we'll be, for the first time in this lecture series, we'll be looking at how to apply transformers for videos. We have looked at transformer application for text, for images, and now this will be for videos. So in the last few lectures, we were looking at application of transformer, not just for image classification, but for detection and segmentation. But today we'll be back to classification once again, but in the context of videos. So one good thing about today's lecture is if you are kind of aware of the vision transformer architecture, which we have discussed so many times in this series, you will find the overall theoretical understanding of today's architecture, which is called TimeSformer, very easy to understand. So TimeSformer stands for time space transformer. So this was introduced by a paper titled "Is Space-Time Attention All You Need for Video Understanding?" This was again from Facebook. So if you really look at computer vision research, you can see that Facebook has contributed a lot of models when it comes to vision. And they have hosted their work in this GitHub repo with almost 1.8K stars. This paper has around 3,000 or 3,300 or something like that many citations. It's written in a easy to understand way. Although when you scroll through the paper for the first time, you will see a lot of equations. It will look super intimidating. You may think like this is a math heavy paper, but actually if you zoom in closer, these equations you already know. This is just attention weights. This is softmax function, Q divided by square root of D. This is the keys. So they are just using a complex mathematical notation for just representing ideas which you already know really well. So this paper, in my opinion, everyone who understands transformer will find it very easy to read. It's also a relatively short paper. Although it may look like a very math heavy paper, it's not at all like that. I don't know why the authors chose to, expand mathematically so much about these things in the main part of the paper. If I was the author, I would have probably mentioned this in the appendix. But anyways, we are anyways not doing a paper dissection here. What we'll be doing is we'll try to understand how the architecture of TimeSformer allowed it to pay attention to a different modality, which is video, which involves multiple frames of images, right? So it's a collection of frames. One thing to note here is when we say video, the audio component of the video is not considered. So that is one assumption, one omission that here we have to understand. So when we say video, video without audio, okay? So the basic idea is this: videos are consisting of multiple frames or multiple images. So somehow we have to modify vision transformer such that it can take multiple images as input and construct some sort of modified attention. Because the normal attention in vision transformer, as you know, you have an image which is split into patches. Patches are converted to sequence of patches, which are projected into sequence of tokens. Class token is added, position embedding is added, resulting in token embedding. And then finally, the context vector associated with the class token is used for classification. So here, if you look at how the attention scores or attention weights are constructed, it is between these tokens which are converted into query key values. So if there are 9 tokens, you can have 9 plus 1, 10, including classification token, 10 queries and 10 keys, resulting in like a 10 by 10 matrix, right? So that is what was done in vision transformer, but this is equivalent to one frame of a video. But in a video, you will have multiple frames. So that is what we are trying to figure out today. And one more thing to note is here the classification token in a vanilla vision transformer is used for classifying the entire image. The task that we will be working on for today's model understanding will be classification only, but classification of an entire video. So we'll be using a specific data set called Kinetics 400, which we will discuss in detail after a bit. Basically, this is a data set of 400 different actions performed by humans. And each video is like 8 or 10 seconds long. I don't remember exact duration, but very short videos where people are performing some actions. That is what is there in the training data. And this entire video can be split, can be classified into one category, one type of action. Action could be running, lifting weight, whatever. Now, if you think about how you classify a video, right? Let's consider two different exercises, something like if you are working out in the gym, biceps curl, where you hold two dumbbells and you curl so that your biceps are getting worked out, versus another exercise which also involves two dumbbells. Now, if you look at one frame of, let's say, biceps curl versus another frame of the second exercise, just by looking at one frame, maybe you won't be able to classify what that video is, even as a human. Because if you look at one snapshot of biceps curl versus, let's say, I don't know, Zotman curl or something like that, it may look very similar if you just compare between one frame from each of those videos. So for some videos, you really need the temporal information. You need information across time more than information across space to perform the classification, because at any given snapshot, these videos may look like the same. But in some videos, you really don't need temporal information that much. For example, if you are, let's say, if it's a video between basketball and volleyball, to classify whether something is a basketball video or volleyball video, you don't really need temporal information. You don't need information which changes with time. Even one snapshot is enough to capture the fact that this is related to basketball or this is related to volleyball. So there are different videos in which sometimes temporal information plays a major role. Some videos where spatial information plays a major role in defining what that video is. So we will see how TimeSformer takes both of these into account, both temporal information and spatial information. What do I mean by spatial information? You look at just one frame, divide that into patches, then convert those patches into tokens and construct an attention score between those patches. This will be purely spatial. On the other hand, let's say you are considering one patch here, and then after this is, let's say, frame T, and this is, let's say, frame T plus 5, and you are considering the same spatial patch, but after few frames. Now, if you are looking at constructing attention score between this and this, then it has temporal nature. It is an attention that spans the time dimension. So we will see how this is done, how computationally expensive this is, how can you make this more efficient, etc. And we'll also try to implement one from scratch. So first, think about video. A video will be unlike an image. It will have one more additional thing, which is F for frames. So width multiplied by height multiplied by number of frames. So the number of pixels in the image would be W times H. So this is the total number of pixels. So this will depend on the resolution. And the F will decide how big the video is. If you have more frames, it's a longer duration video. Now, let's try to just do a quick calculation of the total number of spatial tokens. Spatial tokens, if we denote it by N, you know that it's along the width. If patch size is P, along the width, there will be W by P, that many number of patches. Along the height, there will be H by P, that many number of patches. So total number of patches will be number of patches along the width multiplied by number of patches along the height. So it will be WH by P square. If it's a square image of equal size on both dimensions, it will simply look like image size by P, the whole square. So this is what the number of spatial tokens, what it looks like. Number of temporal tokens is how many tokens can you construct along the time dimension. That will be simply equal to F, where F is the number of frames. In each frame, you can construct spatial tokens, but the total number of temporal tokens will depend on total number of frames. And the overall number of tokens will be a product of these two plus 1. So plus 1 to account for classification token. So we will be adding one CLS or class token so that we can classify this whole video. So the total number of tokens which represent one video will be N times F plus 1. If this was just an image which was passed to vision transformer, it would simply be N plus 1. F won't be there. F will be equal to 1. So in vision transformer, number of tokens equal to number of patches plus 1. Okay, just keep this in mind. We will come back to this a little bit later. Now, I want to show you a few different attention types that the paper discusses. So this figure I have taken directly from the paper. Don't feel intimidated. It's very simple. So we will be looking at it column by column. So first we will focus on this column, then we'll move to this column and so on. So now here, what they are showing is 3 frames, frame number T, frame T minus delta, and frame T plus delta. So basically this is the current frame. This is the next frame. This is the previous frame. So all of these are previous frame. Now just focus on this part. Okay. If we are constructing a purely spatial attention, okay, and now consider this blue color patch which is projected into query. I mean, the blue color represents the fact that it is the query that you are currently considering. Which are the tokens other than itself, which will be converted to keys? All of these tokens or all of these patches will be converted to keys, right? So all these will be keys which the query will try to pay attention to, including itself. Now, this is purely spatial attention. And in cases where, just like the example that I mentioned, if the video is fully spatially informative, like basketball versus volleyball, then probably you don't care about temporal dimension at all. Even this might be enough, correct? But let's say some videos which are highly dependent on both spatial and temporal information, you could construct something called as joint space-time attention, which in the paper they denote by this term ST, S for space and T for time. Now let's see again what this represents. Here, blue color, this is the query, this is the token that is converted to query. And all these red color patches are those tokens which can be projected into key space. So now this query can pay attention to itself, plus it will pay attention to every single tokens. Okay. So total number of tokens that the query can pay attention to will be equal to total number of all possible keys in this entire corresponding to this entire video, which means every single patch in every single frame will have to be considered, along with, of course, classification token. But this is, as you can imagine, we will do the exact calculation in a little bit of time, but you can imagine this to be very computationally expensive, because look at the total number of possible query key pairs. For this query, all the keys are its pair. For this query, all the keys are its pairs. So you can construct large number of query.key transpose such calculations. So the order of magnitude of the complexity of attention calculation is very high in this joint space-time attention. But joint space-time attention, it may give you the most context-rich information, because, I mean, at least that's what you will think, because you are considering every single patches. What this paper, on the other hand, proposes is this idea of divided space-time attention, which they denote by this T plus S term, temporal plus spatial, not space-time, it's just space and time separately. So what they do is they construct attention score separately. So here, if this is the query, okay, this query is in the time frame T. So when it constructs spatial attention, this query will be looking at all these keys which are denoted in a red color, including itself. Okay. So this is spatial attention. Why? Because we are not looking at different time frames. We are looking at the same time frame. But this is not good enough, because here there is no information about what is happening across time. So to take that into consideration, what it does is it constructs a separate attention score called temporal attention, where temporal attention allows this query to pay attention to this key. So this key is the key which resulted from the exact same patch. So this was patch number 0, let's say. This is also patch number 0, but in a different time frame. Same thing, this key can pay attention to, this query can pay attention to this key, where this key is again resulting from the same spatial patch, but different temporal patch. So it can construct divided space-time attention, where you first calculate spatial attention and then you calculate temporal attention to overall get information across space as well as across time. We will go through this in a little bit of detail soon. I just want to first show you the figure. Two more attention types that the paper discusses, which we will quickly go through. One is called sparse local global attention. So sparse local global means if you look at this as the query, these are the local patches corresponding to the query, and you can see that this attention is constructed with these local patches in space as well as in time, because the same local patches are there in this frame, same local patches are in this frame. But the good thing now is the temporal attention is local patches are simply decided based on how many patches you want surrounding your individual pixel. So if you say surrounding your individual pixel, you pick all the immediate neighbors, then all those immediate neighbors will be local patches. Then if you say all the pixels which are 1 pixel away from the immediate neighbors, and that too you pick from that in a sparse way, they can be called as global. So here local will allow you to pay a little bit of local spatial attention, and you can also construct temporal attention because now you are only looking at a few number of query key pairs across time frame. On top of this, to get global information, you also construct these global patches, which are not immediate neighbors. They are 1 step away from the immediate neighbors corresponding to query. But you will not be picking every single patches because that will increase the computational complexity. But this global attention will be sparse. So that is why sparse local global attention. So this is another idea which the paper attempted. The last idea was something called axial attention, where spatial attention will be constructed through this y-axis and x-axis. Temporal attention will be on the same patch. Now, the paper has attempted all these 5 different types of attention, and they have found out the divided spacetime attention to be most beneficial or the best in terms of performance accuracy. We will look at that after some time. We will also discuss briefly why, unlike we expect, why this was not the best performer, why joint spacetime attention did not perform the best, why divided spacetime attention performed the best. We will briefly discuss. And these are the corresponding transformer block architectures. It's very simple. So ZL-1 is the context vector coming from the previous transformer block. ZL is the context vectors resulting from the current transformer block. The name of the paper is this one, is Space-Time Attention, All You Need for Video Understanding. You can simply search TimeSformer paper on Google to get the paper. Now, in between, look at what's happening. Space-time attention is applied, followed by multi-layer perceptron. Space-time attention is attention across all the patches in space and all the patches in time. Now, there will be, of course, layer normalization, which the paper is not showing for simplicity. But when we are implementing this from scratch, of course, we have to implement layer normalization also. And these are residuals. In joint space-time attention, space attention is simply in one frame. I think I mentioned in space as well as time. That is the space-time attention. Space attention is just in the space for one frame. Space-time attention will apply joint space-time attention across all patches in the current frame as well as previous and past frames. Divided space-time attention, just pay attention to this particular architecture because this is what we are going to implement today. You have the context vectors resulting from the previous transformer block. Then first you apply time attention, then you have residual, then you apply space attention, then you again have residual, followed by multi-layer perceptron, followed by residual, resulting in final context vectors. Only detail that is omitted here is the layer normalization. Sparse local global attention is same thing. First you apply local attention using the immediate neighboring patches. Then you apply sparse global attention with the patches slightly away from the immediate neighbors, followed by multi-layer perceptron. Axial attention is first you apply time attention, then you apply along the x-axis, then you apply along the y-axis, followed by multi-layer perceptron, resulting in final context vector. So we don't have to spend any time on the architecture. Architecture part is very simple. In any case, this is what we are going to implement today. First time attention and then space attention. Now let's spend some more time just reading a few points about space attention. So in space attention, as you know, every patch looks within the same time frame. It will not look across the time frames. And as I mentioned, this is where appearance of the data set matters the most, like volleyball versus basketball. If that kind of classification is only what matters, it doesn't matter whether you have the time information or not. Only space information is needed. Joint space-time attention is where both time and space information are required to have the highest expressive power. But as you know, this computational expense is very high, and we will come to discuss why it is scaling as the square of n multiplied by f, where f is the number of frames and n is the number of patches. So this we will discuss in a little bit. But space-time attention, if the video length is very high, this is impractical because number of frames f will be very high. If it's a high resolution image, then the number of patches n will be very high. So this joint space-time attention is impractical for long format videos and high resolution videos. Then this is a plot which the paper shows about the divided space-time attention versus joint space-time attention approach. We can focus on any one of the plots. So let's look at plot B, okay? So what they're showing is, on y-axis, it's showing teraflops. So flop is floating point operations per second. So floating point how many floating point operations per second is required is an index of how complex your model is. So here, as you can see, if there is a joint space-time attention as shown by this purple color graph, you can see that as the number of frames increase, as the number of frames in your input video increase from 32, 64, 32 frames is simply what? A 1 second video, right? Normal FPS of a normal video that we watch is 24, 30 frames per second. So this is just like a equivalent to 1 second video. This is equivalent to a 2 second video, right? This is like a 3 second video. So the moment the video length is a bit high, the teraflops operations that are happening will go out of memory. So these calculations are difficult to perform in joint space-time attention, whereas in divided space-time attention, there is such a scaling of, quadratic scaling of computational complexity is not there. Still, there is a linear scaling. We will come to discuss why it is linear with respect to number of input frames that we can discuss. But divided space-time attention, in terms of computational complexity, is much less complex. So this we already discussed. It will reduce the complexity, but we are yet to discuss by how much it reduces. So now let's try to do a quick calculation. Okay, so this figure nicely summarizes everything. So you have multiple frames. If you are paying attention within one frame, it's spatial attention. If you are paying attention within that one frame as well as within the same patch in different time frames, it is spatial plus temporal attention. Now, these equations, which I directly took from the paper, these are exactly the same equation. It's just that their notations are different. In one case, they have notation through space as well as through time. In space only attention, they have notation for just spatial patches. Here, they have only for temporal patches. So we will be implementing this and this, attention across space and attention across time. And then these will be part of the transformer block. I don't want to go through this notation. I mean, it's very boring, but I think you know already what's happening. Your attention weights are query multiplied by the dot product of key divided by square root of d, so that you are normalizing, and then you take the softmax so that attention weights are attention scores are getting converted to attention weights. And sparse local global attention, as I mentioned, it tries to first apply local attention to nearby patches and then sparse global attention to one level outside patches. Axial attention also we discussed, so let's not spend time on this. Now I want to spend a little bit of time on calculating attention complexity. Okay, so let me not show you the equations first. I can ask some questions. So let's try to calculate the attention complexity. So the order of magnitude of complexity of attention calculation will be proportional to order of number of query key or query.key transpose multiplications that we require. I think this we had discussed in Swin transformer lecture. So number of query.key transpose multiplications that we require will decide the complexity of the your attention calculation. Now the question is, how many queries and how many keys will we have? Okay, so let's first consider joint space-time attention, where it's not divided. It's like we are considering all the patches across all the frames. Okay, so let's say the number of patches is equal to W by P, where P is the patch size, multiplied by H by P. This is the number of patches in one frame. Okay, so N equal to W by P multiplied by H by P. Then number of temporal patches. So this is spatial. Number of temporal patches equal to F, where F is the number of frames. Now, can you tell me how many possible queries are there total? How many possible queries? Q equal to what? How many queries are there from which I can, from which I can pick a random query? I can see a lot of answers. Some people are saying N plus F, NF, W by P multiplied by H by P multiplied by F, Fn. So just think about this. Your query can involve any token in your sequence, and these tokens can come from current frame, previous frame, next frame, etc. So in each frame, you have n spatial tokens and you have f temporal tokens. So obviously you have nf. Total number of spatial multiplied by temporal tokens will be nf, but we are missing one thing, which is the CLS token, right? So classification token also we have to consider. So these many possible queries are there. How many possible keys are there? Same number of keys, because these same tokens can be projected into the key space also. So nf plus 1. This is in the case of joint space-time attention. Okay, it's not divided space-time attention, which means the total number of possible query dot key transpose calculations that are possible are nf plus 1 multiplied by what? Multiplied by nf plus 1. And typically the product of n and f, so the attention complexity will be on the order of this, and typically the product of nf will be much greater than 1, which means this we can approximate to be nf multiplied by nf, which is nf square. So this is why the complexity of our attention calculation will be a square of n, or it can be a square of f, or it can be a square of nf. So n is the number of patches, which, or let's not talk about n, let's talk about f. F is the number of frames, and just focus on this graph, which I showed you in a while ago. Just look at this graph. This graph, the order of complexity of calculation is kind of quadratically increasing with number of frames, right? So this is basically f. X-axis is f. Y-axis is a proxy for order of complexity of attention calculation. And you can see that it's growing quadratic with respect to f. Okay, so this is the calculation for joint space-time attention. Obviously, you can see that it's very complex. So order of nf plus 1 whole square, which is approximately order of nf square. Now let's talk about divided space-time attention. In divided space-time attention, first we apply time attention, and then we apply space attention. So let's first discuss how many temporal tokens are there which can be projected into queries. The total number of possible temporal tokens will be f plus 1. So this classification token can be considered as either, it's considered as both, because classification token is just for final classification. It's neither exclusively belonging to time nor exclusively belonging to space. So if F is the total number of tokens, the F is the total number of temporal tokens, the total number of temporal queries that are possible. So temporal queries that are possible are F plus 1, where F is the number of frames. Similarly, how many spatial queries are possible? So here actually, okay, for those of you who are saying n, where n is the number of patches, yes, it's a good way to think, but it's actually n plus 1, because in spatial query also, when we are projecting like the temporal, when we are projecting the patches into query space, we can also project the patch corresponding to CLS token. Okay, we can also project the token corresponding to CLS token into the query space as a part of time, also as a part of space, because CLS token is neither temporal nor space. It's just used for classification. So total number of temporal queries, we have F plus 1. Total number of spatial queries, we have n plus 1. And which means total number of queries possible is how many? This is divided space-time attention. Total queries possible will be we're just talking about just total number of queries. It will be actually it's n plus F plus 2, simply because when we are constructing these queries, this once temporal query calculation is done, you have F plus 1 possibilities. When spatial query calculation is done, you have n plus 1 possibilities, and they are anyway done separately. Temporal attention and spatial attention are done separately. So you may think we are double counting the CLS token, but it's not like that. We are simply saying the fact that the CLS token, how temporal queries are taken, please show it in the diagram. So temporal queries, you will understand when we are coding, because all we can say is, if you look at this diagram, see, these are the patches which are used for calculating the temporal query. This one, and this one. So this will be converted to, let's say, 768 dimensional vector. This will be converted to 768 dimensional vector. This will be converted to 768 dimensional vector. And if the query key value space is, let's say, 64 dimensional, this will be projected using WQ matrix to 64 dimensional vector. This will also be projected to that 64 dimensional vector. This will be also be projected to 64 dimensional vector, right? Because from the temporal dimension, we are only considering at any given point one patch each. In spatial dimension, we are considering all these patches from the spatial dimension. Will temporal patch be used as query or key? Both. Yeah, I'm coming to that. So, all right. So total number of queries possible are n plus F plus 2. Now, let's say total number of keys possible. How many keys are possible? Same number of keys. So you are saying n plus F plus 2 keys, right? So one way to think about that is, it's like this. Okay, I said query here. Let me remove this and say keys. So keys, you guys are correct. These many keys are possible. Temporal keys are, I wrote query, please note. Here I meant to say key, not query. So total number of keys that are possible in temporal dimension is F plus 1. Total number of keys that are possible in spatial dimension is F plus 1. And total, which means total keys, not queries, is n plus f plus 2. Now my question is, it was not how many keys are, I just blanked between query and key. My question is total number of queries possible when we are constructing attention. The total number of queries possible are coming from your entire token. Your query can be basically any token in your sequence. But when you are constructing temporal attention, those queries will only pay attention either temporally at any given point of time or spatially at any given point of time. So total number of queries that are possible are equal to total number of tokens. Because as a query, you can basically pick any token. Like for example, if let's say I pick this as my query, okay? So if I pick this as my query, my temporally, this query can pay attention to this and this, okay? And spatially, this query can pay attention to all of this. So my choice of number of possible queries, okay, I can basically pick any of these as the query, but choice of keys will depend on whether I'm applying temporal attention or spatial attention. So let me explain that once again. My choice of key is any possible token from my list of tokens. How many tokens do we have? We already discussed this a little bit before. Totally, how many tokens do we have? We have nf plus 1 tokens, right? So totally we have nf plus 1 tokens. So any of that nf plus 1 token can be my query. Now, depending on whether I am picking temporal attention or spatial attention, the number of available keys will differ, which means I have to calculate the number of keys differently, which we already did here. So number of keys in the temporal dimension will be number of frames plus one to account for the fact that classification token can also be a key. Number of keys along the spatial dimension is n plus 1, where n is the number of patches in the current frame, plus 1 to account for the fact that CLS token also can be considered as a spatial token. So total number of keys possible will be n plus f plus 2. Total number of queries from which you could pick was nf plus 1, which means what would be the order of magnitude of your complexity? It will be product of these two. So it will be nf plus 1 multiplied by n plus f plus 2. Now, how do we simplify this? Nf plus 1 is approximately equal to nf. N plus f plus 2 is approximately equal to n plus f, because both the values of f is actually 8. So f is not significantly greater than 2. But let's say if we had a longer frame video, n plus f plus 2, we can approximate to be n plus f. So order of magnitude of this will be roughly, order of magnitude of attention complexity will be roughly nf multiplied by n plus f. Now, what we can do is, how does the attention complexity scale with respect to f? So earlier we had a graph where y-axis was order of magnitude of attention complexity, x-axis was f, where f is the number of frames. So based on this equation, can you say whether the attention complexity with respect to f, okay, as f increase, does the attention complexity increase linear to f? So attention complexity is definitely quadratic with respect to f and n separately. But what is mentioned in the paper is that it's like a weird term. So I just want to show you that figure. Then you will understand Where is that? I think it's in the previous figure itself. Divided space-time attention. Oh, not here, not here. So per token, okay. So totally how many tokens do we have? Total number of tokens is proportional to NF. It was actually NF plus 1. So total number of tokens was proportional to roughly NF, right? N is the number of tokens in space, F is the number of tokens in time. So if you look at the joint attention complexity, it was quadratic in NF because joint attention complexity was NF square. But if we talk about how is the attention complexity growing per token means this thing you have to divide by NF because one token, the total number of tokens are NF. So per token, your complexity grows as NF. So just to reiterate once again, the total attention calculation complexity in joint space-time attention calculation was NF the whole square. But this is not per token. This is for all tokens combined. But totally you had how many tokens? You had approximately NF tokens. So if you want to calculate attention complexity per token, this number you can divide by NF because NF is the total number of tokens, which means the resulting number will be NF. So the attention complexity is proportional to NF per token in the case of joint attention. In the case of divided attention, it is linear in N plus F per token. Why? Because the attention complexity in divided space-time attention was NF multiplied by N plus F approximately. And if we want to calculate the attention complexity per token, we can divide this by NF because NF is the total number of tokens, which means the resulting number is approximately N plus F. So as each token, as you have one token increase, the attention complexity will increase by N plus F. Whereas if you had joint attention, as you increase the number of tokens by 1, your attention complexity will increase by the product of N and F. Overall attention complexity in one case will be NF, N square F square. In the other case, it will be N square F plus F square N. So this is for joint. And this is for divided space-time attention. Okay, so this is the difference. And this plot, okay, now let's try to reason whether this graph is supposed to be linear or quadratic. Can you guys try to reason the complexity as a function of F? Now, do you think this is actually a linear graph or quadratic graph? I mean, mathematically, based on the logic that we have discussed so far, the order of magnitude of complexity, I mean, this is not per token. I mean, x-axis is F only. So let's say x-axis is input number of frames, which is equal to F. Okay. Attention complexity, is it scaling as, if it is linear, it will basically just be scaling as alpha F. Attention complexity will be scaling as alpha F. But is it scaling as alpha F or is it scaling as some beta F square? There is definitely an F square term, right? Because the attention complexity was F square N plus N square F. So definitely this graph is mathematically it's quadratic, but it may look linear. This one is a better representation. So now let's look at this. Here, spatial crop. So I think spatial crop P is the patch size, if I'm not wrong. As patch size or number of patches? Number of spatial crop size in pixels and number of input frames. Okay, I don't understand why if patch size increases. Okay, I don't think this is the patch size. I think this is the image pixel size itself because patch size was 16 by 16. I think this is the image pixel 224 by 224. Okay, now let's calculate this. If image size doubles, let's say image size becomes W and H becomes 2W and 2H. Okay. What happens to the attention complexity in joint space-time attention? Will it double or will it quadruple or will it be something else? Basically, will it be linear or quadratic? If this axis doubles from 224 to 448, if it goes, will the attention complexity double or will it become 4 times? So attention complexity was nf the whole square. Now here f is not coming into picture, f is kept constant. So it is proportional to n square. N is the number of patches, and we know n depends on wh divided by p square, wh by p square, the whole square, which means this is proportional to w square h square, and w became 2 times, h became 2 times. So this will be 2 times 2 equal to 4x. So instead of the complexity becoming 2x, it became 4x. So it's not linear, it is quadratic. Just 4 times does not mean it's more than quadratic. That's not the case. It became 4 times because your input became 2 times. So input became 2x, output became 4x, which means the relationship is quadratic. Now, this is the case with joint space-time attention, this graph. What about divided space-time attention? In divided space-time attention, it was n square f plus nf square. So here also there is a quadratic term. So overall, it will again grow quadratically, but at a less faster rate. So w square, yeah, this is correct. Yeah. So yeah, proportional to, so this will be 4, this will be 4, 16. Whereas n, the total image size became, in terms of pixels, it became 4x because height increased by 2x, width increased by 2x, which means total number of pixels grew by 4x. But the total attention complexity grew by 16x, not 4x, 16x. And 16 is 4 raised to 2, square of 4. So attention complexity is square as a function of image pixel number, but it's quadratic if you just look at, instead of pixel number, if you're just looking at width or height, it will be, of course, raised to 4, okay? But usually the number of pixels is the product of width and height. So as the number of pixels doubled, attention complexity quadrupled in both cases, because it's just that these are both quadratic graphs, but one is growing faster than the other. All right, so that is about divided space-time attention. Now, few more things to discuss before we can start coding. So this plot is again taken from the paper where they did something called TSNE. It's a technique using which you can reduce the dimensionality of your embedding. So what they are displaying is they have reduced the dimensionality of the embedding. I think original embeddings are of 768 dimensions. Okay, so every single image that you have as an input, or sorry, every single video that you have as an input will be converted to embedding in the form of your classification token. That classification token will be of 768 dimensions. Now, those 768 dimensional tokens you can convert into using dimensionality reduction technique TSNE, you can make it into 2-dimensional token. And when you are plotting that 2-dimensional token, you will get a 2D sort of like scatter plot like this. Now here the colors show different classes. So different classes meaning different actions people are performing in the video which was used for training. So if the video was kinetics 400 video, it will be like different actions performed by humans. So what you can see is if we just use a vanilla vision transformer where we are feeding just some frames and converting those frames into CLS tokens, then CLS token is converted into 2 dimensions using TSNE. You can see that the green color tokens, which are belonging to the same class, are everywhere. So you can see a bunch of green color tokens here. You can see a bunch of green color tokens here. Here also there are a bunch of green color tokens, etc. Whereas TimeSformer with space attention has a better clustering of these tokens. Here you can see one giant purple cluster. Here you can see a cluster of blue, and dark blue. Here you can see a cluster of light blue. And if it is divided space-time attention, you can even see better clusters emerging. So clusters emerging meaning the classes which you have, which are actions performed by humans, maybe running, jumping, whatever are the actions in the kinetics data, the embeddings corresponding to the classification token, which represent these classes, those embeddings have very good spatial separation. That's the reason why these nice clusters are emerging, meaning the 768 dimensional token, if you reduce it to 2-dimensional tokens and you represent them by 2D points, all the data points, right? So these are all the data points which the which the model was used to train on. Those data points are forming nice different clusters. If these clusters did not exist, what does that mean? Can anyone mention in the chat? If the clusters were not there, if all these dots were equally spread out, what does that mean? It means your model might find it very difficult to perform classification, because your embedding at the end of the day, see, this is what we are doing, right? When we are performing classification, we are ultimately converting everything into vectors. If they were 2-dimensional vectors, and let's say it was a binary classification, we basically need clusters where these 2 points may be corresponding to class 1, and these 2 points should be corresponding to class 2. This is when a nice hyperplane can be formed between these classes that separates them. But what if, so this is class 1 and this is class 2. But what if these 4 points are formed such that they are kind of like closely located to each other? The kind of hyperplane that you have to form might be very complex. We don't know, right? So ideally, for separation using hyperplanes, you need classes to have very good spatial separation in whatever dimensional embedding space you are considering. So here you can see that when we use TimeSformer with divided spacetime attention, these nice clusters are emerging, which are just a representation of how well apart spaced are individual classes in your training data set when they are represented using the classification token. Because at the end of the day, this entire video is represented using just one vector, which is the classification token. And in TSNE, the entire video is represented using just one dot. So this one dot is one video. Okay. And the fact that these green dots are nicely separated out, or you can see more number of visible clusters here than here, shows that divided spacetime attention is indeed helpful for performing better classification on videos. So visually you can see that here there is better clustering than here. Here all the clusters are merged together, which means classification through hyperplane formation will be very, very complex. This is just the result from the paper, and this is where one surprising thing was there. So while reading the paper, I was expecting the paper to say something like, joint spacetime attention, because it has the full context, it will perform better. And on the kinetic 400 dataset. So this is another dataset called something V2. We are not going to discuss this, just kinetic 400 dataset. On that, divided spacetime attention is giving the highest classification accuracy. Joint spacetime attention is giving 77.4% accuracy. There are multiple reasons. One is, of course, the number of parameters in the model that they used is a bit less. It's 85 million parameters versus this is 121.4 million parameters. So obviously, it's not an apple to apples comparison. It's two different models, so you can't really compare. But another thing is, in divided spacetime attention, to create your query key and value, you have actually two different weight matrices: WQ temporal, WK temporal, and WV temporal. Then this is for the temporal attention. For space attention, WQ spatial, WK spatial, and W value spatial. So in divided attention, both of these matrices exist. In joint spacetime attention, this temporal spatial distinction is not there. It's simply WQ, WK, WV for projecting your tokens into query key value space. So one reason why you can argue that although here the full context is not available, meaning the entire temporal information we are not considering, still this is better because you have separate learnable parameters for spatial and temporal information. Whereas in the joint spacetime attention, although you have more number of tokens because you are considering the entire temporal tokens, you don't have separate learnable parameters for space and time separately, whereas here you have separate learnable parameters. So qualitatively, you can say something like this. But I also would like to see a table like this where either this is reduced to 85 million or this is increased to 120 million, so that we have comparable model and see still if this divided space-time attention performs the best. I'm not sure. I'm sure they have done it. Maybe it's mentioned in the appendix. So, but this is the result from the main paper. All right. Now, they also have one more graph just to visualize attention. So you might have seen, this is actually, by the way, very easy to visualize. So here you see corresponding to this frame, you visualize in this highlight. So here you can see bright color patch overlapped on top of your image. That bright color patch is a visualization of your attention map. In which part of the frame is the attention scores being constructed in the highest way. So here you can see that wherever in the frame some action is happening, there is the highlight of the attention coming. So here, where the Rubik's cube is, there is the highlight of the attention. It's not here. If this highlighted patch was somewhere here, then you know that the attention mechanism is not looking at the right place. But here you can see that the attention mechanism, it's paying attention to the right place of this frame where some action is happening. And here also you can see attention mechanism is giving the most highlight to region in the image where most amount of information is occurring. This is a technique which is also used in explainable AI, like you might have seen this line images, or not this line, explainable. You might have seen these images where you can construct regions where the most prominence is there for classification or whatever task you are doing. So this color map overlaid on top of the image tells you where the model is primarily looking at. And similarly, you can also visualize attention map visualized vision transformer. This can be done in literally like one line of code, or if you go to Dino V3 website, you can see their attention map visualization very nicely. Yeah, you see, this is them highlighting where the model is paying attention to. Yeah, you see this one. This is not the exact same technique, but this is one way in which you can visualize attention. And here you see original image is this bright color highlighted region is where the model is paying the most attention. So you can very nicely visualize this to see whether your model is actually doing what it is supposed to do. And this is just an example of that. Kinetics 400 dataset is like a very big dataset. If you go to Kaggle, if you type Kaggle Kinetics 400, you can see the dataset. Okay, let's just open this. And you can randomly open some videos. Okay, this is test dataset. I don't want test, I need training data. So yeah, this one, let's say. So these are a bunch of actions like auctioning, arm wrestling. So let's say I open arm wrestling. I can just open any random video. It will be like an arm wrestling video of like 5 or 10 seconds or something like that. Yeah, 10 seconds. Right. So this is the kinetics data set, and these are the different classes. There must be 400 classes totally. Obviously, we are not going to implement 400 class classification. We will only implement a 2-class classification. So I have created a data set where I have downloaded 2 classes. One was, I think, I have to check the folder. What was the two folders that I downloaded? But I can just quickly show you my data set. Yeah, one is bench press data and another is deadlift. So can you see this? Can you see my screen? Like not the Miro board, but my folder. Okay. So these are the random videos of people bench pressing or deadlifting. And one more thing that I have done is I have written a Python script which can extract the frames of this video. So from each video, it will extract individual frames. So these are now images of certain resolution. Okay, so this is now how my input data set look like. And this input data I have, so in the bench press data, I have only very few videos, just under 60, 60 or 64 videos, right? Yeah, 61 videos, 61, 62 videos. And in deadlift also, I have only 32 videos. So it's like a very small data set. If you remember when we trained Vision Transformer, we had a folder with 60,000 images. So here the size is not that big. So obviously we cannot train the model and expect it to have very good accuracy. Plus in each video folder, I have extracted how many ever number of frames were there in the video. And there also I have sampled, because if it was a 10-second video, it will not be just having 32 frames. It will have a lot more frames. But I'm anyway going to use only 8 frames, because if you remember from this plot, even at 16 frames, the computational cost was very high. So here you could see that 16 or even 32 frames, the computational cost was becoming kind of prohibitively expensive. So we are going to build a very small model. All right, so now we can start writing the coding TimeSformer from scratch. I will share the Google Drive link first, so that, I mean, I recommend you to code with me, but in case if some lines of code are different and something is not working, you can refer to my code. All right, so this is the link. So now let's start with basic things. So first we need to install a few things. So just do pip install. Before that, just put this exclamation pip install. Torch Vision, I think most of you will have, but I had to install it because it was not there in my system when I was trying this for the first time, although I have used it many times. Then Tim for importing pre-trained vision transformer. So here we are going to use a vision transformer which is pre-trained on ImageNet dataset. So in the hope that we will get a better classification accuracy, because if we start training the vision transformer from scratch, I don't know if the accuracy will be so good. On MNIST dataset, if you remember, we had done training from scratch and we had got like 96% validation accuracy, but this is not as simple as MNIST dataset. Then we need something called Einstein operations, EINOPS. This is for reshaping some of the lists that we have. So just install this, should not take you more than a few seconds. Then we will import a few things. So import OS. This is for creating a folder structure. Import torch, PyTorch. Tim is for importing the pre-trained model from PyTorch. So we need pre-trained vision transformer. Then import torch.nn as nn. This is required for nn.module. Then import torch.utils.data. Okay, from torch.utils.data, import dataset, comma data loader. So this you will need for creating the batches. Then from torch vision, import transform. This is for data transformations like random cropping, random rotation, and any other normalization operation. Then from Einstein operation, EINOPS, import rearrange. So this is to change the dimensionality of our input. Then from TQDM, import TQDM. TQDM is to display the progress. The full form of this we had discussed in one lecture, Takadum or something, like some Arabic word. Yeah, this is the word with root in Arabic. It means progress, basically progress bar. Import Tim. I don't know what is the full form. Full form of Tim in Python. I don't know if there is a full form. Python PyTorch. Okay, torch image models. So TIM stands for torch image models. Okay. That's it. I think mostly that's it. Yeah, one more thing we can do is device equal to CUDA if torch dot CUDA dot is available, else use CPU. All right, so just run this, and I would rather run on TPU. So I'm just changing the runtime. I don't think you will have the TPU access, so you can use whichever is the best, best option that you have. But if you have TPU, go for it. Then, okay, so now the next part is you will require access to a Google Drive folder. So let me just share the Google Drive folder 1 second. The Google Drive folder where the data set is added. So just give me a second to locate the folder. All right, so this is my folder, exercise data. I will make sure that anyone with the link has access. So do one thing, make a copy of this folder in your drive, because when you are connecting the Google Colab to Google Drive, you will have to connect it with yours. So just make sure that you have a copy of this folder in your drive, okay? And next is, we have to, okay, some error is there. No module named Tim. Okay, so next is creating our training data set from the folder structure. So in my folder, this is what I have. This is the folder name called output. Then I have inside that two classes, bench press and deadlift. And inside each, there are different video folders, video 1, video 2, etc. And inside bench press, I have same structure, video 1, video 2, etc. But inside each video folder, it's bunch of frames that I'm going to use. Okay. So this is my structure. So to convert this structure into my training data format, I need to run a block of code, but that block of code I'm not going to write from scratch because it will be a huge time consumption for us. So instead, what I'm going to do is I will just that block of code alone, I will run by copy pasting. So this is the class that I have defined to convert the video frame into data set of train label format. Okay, I think I have to import image also. We'll see. Next is we can define the transformer block for TimeSformer. So this part we will code from scratch. So class transformer block, and of course pass nn.module. Define __ init. And into this we have to pass self and a few more things which we will figure out on the go. Then super for calling the init constructor of the parent. Okay, and now we have two types of attention. How many things are there, first of all, in the transformer block, individual block? These are the things we have to code. We need one temporal attention, one spatial attention, MLP. Then we also need the layer normalization. Residual anyway is done during forward pass. So residual we don't have to define inside the class definition itself. We can do it inside the class within forward function. Okay. So we need four things: temporal attention, spatial attention, MLP, and layer normalization. So self dot temporal underscore attention equal to nn dot multi head attention. So here we are not coding multi-head attention from scratch. We are using it from the nn dot module. And here we have to pass embedding dimension. We have to pass number of attention heads, and we have to in the multi-head attention, and then we have to mention batch first equal to true. Otherwise, by default, sequence will be the first 0th dimension, not batch, and which means dimension, embedding dimension, and number of attention heads we have to pass here. And same thing, spatial attention is also exactly the same thing, except what we will be passing will be different. So spatial attention will be same multi-head attention of same number of dimension, embedding dimension, same number of heads. Then we can define layer normalization. So self.norm1. So we need one layer normalization associated with temporal attention, one associated with spatial attention, one associated with multi-layer perceptron. So this is equal to nn dot layer norm along embedding dimension, and this copy paste this 3 times and change this to norm 2, norm 3. So we need 3 layer normalization. We also need to define MLP. So self.mlp is equal to nn.sequential. So we are defining the input layer, which is nn.linear projection from embedding dimension to 4x dimension. So dim comma dim multiplied by 4. And then there is a activation, which is JLU, nn.JLU activation, followed by projection back from 4x dimension to original dimension. So dimension multiplied by 4, comma, dimension. So in MLP, you project your embedding into 4x dimensional space, and then you project it back. That's it. The transformer block is done. Then define forward pass. Define forward self, comma, input x. Then in the forward pass, first we have to get the dimensionality, different batch dimension, temporal dimension, number of patches, etc. So batch, temporal, n for number of patches, d for embedding dimension is equal to x dot shape. So this will be inside the input x, b, t, n, d. Then we say, now what do we have to do? First of all, we have to pass this through temporal attention. So, and then do layer normalization, then add residual, then spatial, then pass through spatial attention, then do layer normalization, then add residual, then pass through MLP, add layer normalization, add residual, and then you get the output, right? So this is what you have to do. So first x temporal, xt, so this is the input that will go into temporal. This is where the rearrange function is being used from the Einstein operations. Rearrange of, we are rearranging x into a certain dimensionality such that currently it is batch, comma, batch time, n for number of patches, d for dimension. This is the way it is. But in the temporal dimension, we don't care about the batch and number of patches separately. So we can group batch and number of patches together, but we need temporal dimension and embedding dimension separately. So here what this does is it will convert the x, which originally has these 4 dimensions, into 3 dimension, where batch dimension and number of patches are converted into one single dimension. But the temporal dimension and embedding dimension. Temporal dimension meaning number of frames. So that the dimension which captures the number of frames, and dimension this captures the embedding space, that will be retained because we are applying attention across temporal dimension. And then we say xt equal to self dot, we copy paste this guy, self dot temporal, into which we have to pass the input which gets transformed to query key value each separately. So xt, xt, xt. And from the output, the 0th index item is the context vector that we are looking for. So now we have the context vector stored in xt, but we have to rearrange it back to the original format. So again, do rearrange this such that input is xt, not x. So xt, comma, copy this, paste it here, but originally it was b n. So batch and spatial patches were grouped together, and t and d were here. But now I don't want that grouping. I want b comma t comma n comma d. But I need to pass a few things here. First, I need to mention what is b, where b equal to batch, because here in the input, the batch and n was in one group. So we have to explicitly tell the function what is the value of small b and what is the value of small n. So value of small n is equal to n, value of small b is equal to b. And after applying temporal attention, we add layer normalization. So x equal to x plus self dot norm1, right? Yeah, norm1 of xt. So we apply layer normalization, then add the residual. So this is the residual, okay? This is a bit confusing because now each patch is attending to each patch in temporal space. That is correct. Only the, so not each patch is attending. In the temporal space, we have a given query, right? And that given query will come from this t comma d dimension. And that query can attend to all the, the query can come from anything. Key will come from this. Key will have a total number of possible keys will be along the temporal dimension. Each key will be of dimensionality d. And query can come from basically any possible patch in your entire input data. And xt I separately denoted so that I can later add residual like x equal to x plus. Otherwise, I would have done something like residual 1 equal to x. And then if I retain the terminology x, I will have to say x equal to x plus residual 1. But we can keep it separate like this. We have used the same xt for query, key, and value. That is a good question. Basically, your question is should we not use x instead of xt, right? This is what you're asking, right? For query, should we not pass the... I think that is logically correct. But I'm just thinking dimensionality wise. Okay, let's do one thing. Let's keep it x comma xt comma xt, because now obviously x and xt will have different dimensions, but I don't think it will cause an issue. But let's see, okay? And now we have to apply the temporal dimension. So spatial dimension, x spatial equal to rearrange x comma. Again, it will have this structure. So b comma t comma n comma d, but this time I'm grouping batch and time dimension. The spatial dimension, which is n, which is number of patches, I'm retaining. And x spatial equal to again, we will go by this logic, but if it results in any dimensionality issue, at that time we'll figure out. So input is X. No, here input should be X, yeah. And input for query should be X. Input for key is XS. Input for value is XS. And then XS, which is spatial, rearrange B, comma, T, comma, N, comma, D, converted back into BT and D, and I have to pass this time B and T because B and T was grouped. So the input has no idea what is B and T separately. So I have to separately mention. And this should be spatial. Yeah, thank you. I think everything is correct. And then we say X equal to X dot. This should be spatial. This is correct. XS is spatial. Is there any other mistake? In rearrange. Oh, yes, yes. Now, is there any other mistake? Everything looks fine. Let me know if anything else is missing. X equal to X plus self dot norm 2 of X spatial. Why do we need to rearrange if we are taking X as the query? Because for key and value, we are only considering from, so this XS is still needed, right? And for XS, we don't care about spatial difference. We don't care about spatial tokens. We want all the tokens temporally. So we need the temporal and embedding dimension separately. So XS we need. Otherwise, if we pass X here instead of XS, it will be as if we are passing all the tokens in this shape into query key value, into be converted to query key value. The logic which applied for XT also applies for XS. So in XS, we don't care about spatial tokens. So spatial tokens are merged with the batch dimension so that, temporal tokens are merged with batch dimension so that only spatial dimension and embedding dimension is remaining. I think mostly this is correct. Then we need to implement MLP. So first is implementation of temporal attention. Second is spatial attention. Third is MLP. X equal to X plus. So again, this is residual self dot MLP. Actually, you know what? Self dot norm 3 of self dot MLP of X. So we pass it through MLP. Then after passing whatever output we get, we add, we perform layer normalization, and then we add the residual. So this is the final output. So now we can return X. So this is not the full TimeSformer. This is just the transformer block within the TimeSformer. But TimeSformer, to have it fully, we should have patch embedding. For dividing into patches, CLS tokens. So those things we need to define. This is just one block, okay? Like this block has to repeat a few times. But let's run this to see if there is any basic syntax issue or not. Everything looks fine. Now we come to class TimeSformer. nn.module and define underscore init, pass self and bunch of other things which we will define in a bit. Super constructor, super for the init constructor of the parent. And so first, self dot number of frames. We have to know the number of frames, which means we will pass that num frames. So that we will pass here, number of frames equal to 8. So this is the default number, but we can pass different number. Then self dot patch size equal to patch underscore size, and default patch size was 16. So we will pass that. So equal to 16. Then self dot embedding dimension equal to embed underscore dim, which means this also we need to pass. So here we have to use the default dimension if we want to use pre-trained vision transformer, because it is expecting a certain dimension. So here it should be 768. But if we don't want to use pre-trained, we can use our own dimensions. Then self dot number of patches. This is equal to image size divided by patch size, the whole square. Image size is not known, so that we have to pass. Image size is equal to 224. Then now we can define self.patch embedding. What did we use for patch embedding? If you remember from Vision Transformer lecture, what idea did we use for patch embedding? To divide image into patches, what did we use? What function did we use? nn.con2d, right? So patch underscore embed equal to nn.con2d. And here the input has RGB. So input channels is 3. Output channels is equal to embedding dimension. Then kernel size is equal to patch size. And what about stride? Kernel size is equal to patch underscore size. Stride is also the same. So, and stride is also patch size. So this is the nn.con2d. If you want to know how this was, how, this 2D convolution produces patches, just go to the Vision Transformer lecture, because we had spent a lot of time on this. But basically, to divide a 2D image into patches of your required dimension, you can use nn.con2d operation. Then we have to define CLS token. So self.cls underscore token equal to nn.parameter. So it will be a learnable token. And torch.zeros, we initialize it as zeros, 1, 1, 1. So batch time number of patches, embedding dimension. So the dimensionality of the CLS token will be obviously embedding dimension. Then we need 2 separate position embedding, 1 for time. So 1 for position embedding along time, 1 for position embedding along space. So time embed, then self dot position space embed. Let's call it as space underscore embed. Because technically the frame, which frame you are at, and within the frame which patch you are at. So those are 2 different information. So it's better to use 2 different position embeddings for space and time. So this will be nn.parameter. Again, this will be a learnable parameter. Torch dot random from normal distribution, 1, self dot number of patches, and actually not number of patches, number of frames, +1. I will tell you why we added +1 here. It is for classification token only, and embedding dimension. So in the position embedding for time, we have batch dimension, we have total number of frames, plus we are adding 1 more extra position for CLS token. So for CLS token, we will not be adding a position embedding in space. For CLS token, we just need to add it in one of the places. So in space embedding, when we are defining nn.parameter, it will not look like instead of number of frames, this should be what? Number of patches. It will not look like number of patches +1, because when we are defining position embedding, we just need to keep it at one position, either at spatial position or temporal position. So space embed and self dot blocks for multiple transformer blocks. So self dot blocks, this is where we call the transformer block class, which we defined earlier. So nn dot module list, and here we can say TimeSformer. What was the name? TimeSformer transformer block, not TimeSformer block. Embed underscore dim, comma heads. We were passing embedding dimension and number of heads, yeah. Which means heads we have to define somewhere. So heads will be 12. And we have to also define depth, which is 12. Depth is the total number of times that this has to repeat. So this has to repeat for blank in range of depth. So how many times is my transformer block repeating is defined by depth. Within each transformer block, how many attention heads is there? Heads are there. That is heads. TimeSformer block would be a better name for this, in my opinion. So I'm going to rename this. Okay. And now I think we have defined most of the things. Okay, layer norm also. So self dot norm equal to nn dot layer norm of embedding dimension. Then we need a classification head. So self dot head equal to nn dot linear. So it will be a linear projection from what dimension to what dimension. In the final class, because just like a vision transformer, here also we are performing classification. So we need a classification head. So here we are projecting from embed dim to classes, which means we have to pass number of classes also. So there was a certain order that I wanted to follow. Image size I will keep here. Patch size 16. Yeah, everything else looks correct. Depth I want to keep. Yeah. Okay, I think now we are ready to write the forward pass function. So define forward self comma x. Now we are actually passing the image through the vision transformer block through the divided spacetime attention. So batch temporal, then n, or rather channel dimension, height dimension, width dimension. So video has these many things. Input video will have, it will be in batches. It will have number of frames because that we are importing. It will have channel, RGB, H and W for number of pixels along height and width. Now we say x equal to x dot view, where we join batch and time, comma c, comma h, comma w. So that when we convert this into patches, we don't care about the temporal dimension. We are dividing the spatial dimension into patches. Then we say x equal to self dot patch underscore embed of x. So here we are calling the patch embed, which we had defined over here. Then after patch embedding, x equal to x dot flatten of 2. So flatten of 2 means, so this is 0 dimension, this is dimension 1, this is dimension 2. So this height and width of the image will combine into a sequence of tokens where number of tokens will be height multiplied by width. So that will be total number of patches basically. So x dot flatten of 2, but I want the embedding dimension which as the last dimension. So I also need to do transpose. So this, if you remember, we had done during the vision transformer implementation also. So transpose 1 and 2. So this is 0 dimension, this is dimension 1, this is dimension 2. So 1 and 2 flips means last dimension will become the embedding dimension. Then we say x equal to x dot view batch temporal. Third one, last one will be self dot embed dim. which means second last we can automatically calculate. So we just need to put -1. Python will automatically calculate what that should be because it has other 3 dimensions. Now we have to add position embedding, excluding CLS position, CLS token. So CLS token we are yet to add here. So we have to add position embedding to X. Because CLS we have not introduced yet. So CLS tokens position embedding we cannot take yet. So X equal to X plus. We have 2 position embeddings to be added. One is self dot time underscore embed, and another is self dot space underscore embed. So we are adding both space and time position embedding tokens here. But we have to pass a few things. First is which all time embedding tokens here. We need everything except the CLS token. So CLS tokens position will be at 0. So I need everything starting from 1 till t. But in Python, if I say 1 till t, it will only count from 1 till t minus 1. So here I have to say t plus 1 because the last one is excluded in Python. And then I need an extra dimension because if you notice in the position embedding, where is that? In the time position embedding, only 3 dimensions are there: batch, number of frames, and embedding dimension. But here actually we have 4 dimensions: batch, time, then space, and embedding dimension. So we need to add an extra dimension. So just add this none. So it automatically adds an extra dimension. Similarly, in space, I have batch, then time dimension was non-existing for this. So just add none so that it adds time dimension to the position. Then I need to pick everything self, no, just this. Yeah. So to the input token, I'm adding position embedding corresponding to time, which is basically frames, and position embedding corresponding to space. Now we have to define CLS token. CLS token. So CLS equal to self dot CLS underscore token. And we need to expand that token to have one more dimension because it also currently has only 3 dimensions. Where is that? It has 4 dimensions, but it has to be copied along batch dimension. So self dot CLS token dot expand. So expand along batch and keep this one untouched. Then self dot number of patches. Then last one was -1. So we are expanding the CLS token along batch dimension and along number of patches. Then CLS equal to CLS plus. So now we have to add the position embedding corresponding to CLS token. So self dot time underscore embed. So position embedding for CLS token was added corresponding to time embed because here there was a +1. So here CLS equal to CLS plus self dot time embed of colon, comma, colon 1, which means it will only pick the first item, or rather 0th item, none, comma, colon. So this is exactly same as this, except here we took all tokens starting from 1 to t. Here we took all tokens before 1. Now we need to prepend the CLS token. So prepend CLS token. So X equal to torch.cat for concatenating. CLS is prepend to X along dimension equal to 1. And then we have to define. So now everything is ready to be passed through different transformer blocks. So now we have to say, I need my transformer blocks here. So for block in self dot blocks, X equal to block of X. So here we had defined in the module list 6 transformer blocks, right? Yeah, 12 transformer blocks rather, because depth was 12. So we are iterating through those 12 blocks one by one. And then extract the CLS tokens. So CLS tokens output equal to self dot layer norm of X. So we are extracting only the CLS token, then return self dot head, where we are passing the output through classification head. This is exactly same as what we did in the vision transformer. So that's pretty much it. So we pass the CLS token through classification head, and whatever we get as a result, we send it as the output. I think we are good to go. Let's just run and see if there is any basic issue. Basic syntax issue is not there, but if there is any logical issue or not, we will see. All right, so that also we defined. Now what is missing? TimeSformer. Okay, yeah, now we have to mount from google.colab import drive. This is for connecting Google Drive. This is where you will need to mount your Google Drive and mention your path. You copied my training data from my drive into your drive. So just run this, and here they will ask you to log in. So this is how you connect your Google Drive. And then we need pre-trained, we need to define pre-trained vision transformer. So ViT equal to TIMM. So this is for torch image models. Create underscore model, then vision transformer base model, and patch 16 model. So patch size is 16. Image size on which it was trained was 224. Then pre-trained equal to true. So this is just defining the pre-trained vision transformer model, which you can use. And then we set it to evaluation mode. So ViT.eval. Now I'll show you how to use this pre-trained transformer, vision transformer in our model. Now we need to write a big block of code, which I won't be writing from scratch because that will take too much time. But this is the part where we define, we basically copy the weights from the pre-trained model into our TimeSformer. So this you better use directly, because this is, you just need to know the structure of the vision transformer to write this block of code. Then what else? Okay, now we can define training dataset. So train underscore dataset equal to, we had defined a class called video something, video from dataset. So this is where we use the class for converting the frames into training data. So video from dataset, and root directory equal to, so this is where you will have to mention yours. So mine is content slash dot slash content slash drive slash my drive slash exercise space data slash output. Okay. So this is my path. Your path would be depending on your folder name where you have copied. To find out the path, all you need to do is like open this, then open this drive, and inside this drive, go to my drive and find wherever your folder is, and then click that, and just you can click on the three dots which will load, and then click copy path, right? So you just need to find your folder here and click copy path, and you can paste that path here. That's what I did. Then number of frames equal to 8. So we are only using 8 frames per video, okay? Then train loader equal to data loader. This is where we use the data loader for creating batches, but here actually there is not much big batch size that we can create. So train underscore dataset Then batch underscore size equal to, I have kept it as 2 simply because in my entire training data, I have only, per image, totally 30 images or something, 30 videos or something. So if I create batch size as 2, I will only have 3 batches to run. So here I have kept a very small batch size, shuffle equal to true. Not that it makes a huge difference here. It doesn't make too much difference because anyway, my batch size is 2. Number of workers, I don't think this makes any difference here, but I'll define regardless if we are running on parallel. So training data set, no such directory. Excellent. Content drive, my drive, exercise underscore data output. I am pretty sure such a folder exists. Okay, I don't have to mention /, right? Yeah, that was the issue. I mentioned / because that's a habit, but yeah, / is not needed, just slash is needed. Then what else? Yeah, just defining the model. So model equal to TimeSformer. This is the class name which we defined latest, this class. This one, TimeSformer. And we have to pass a bunch of things here. Number of classes equal to, we can say length of train underscore dataset, but we know that this is 2. So you can manually say 2 also, but whatever. Then number of underscore frames equal to 8. Then embedding dimension equal to 768. Then depth equal to 12. Heads equal to 12. Rest of the things are defined by default where we define. These are also defined. We don't necessarily have to pass here. Then dot to device. Then we say load. Now we have not loaded this thing yet. These pre-trained weights we have not loaded yet. So load, so call this and pass model, comma, vision transformer, which we had defined somewhere up here. So we have to pass our model, and into that model, we are loading weights from this model. So model, comma, ViT. And optimizer equal to torch dot optim, as usual, Adam W model dot parameters. So trainable parameters are what we are optimizing. And learning rate, we should keep a bit small here. I have tried different learning rates. I'll show you my training accuracy also. It's really bad, by the way. Don't expect 100% accuracy or anything, but we can try different hyperparameters. Criterion equal to cross entropy. So NN dot cross entropy loss, because this is classification. So just run this. Okay, so loaded everything. Now what else? Now it's just the training loop. So this I'll just copy paste. I am running for 10 epochs, but we can reduce also. Then let's keep this maybe 5. So this code is very slow actually. It will take, image is not defined. That is because we have to import image. From Python below. Most of the things are working. The only place where I am expecting some dimensionality issue, if any, is where we, instead of passing XS and XT, we were passing X, which is logical, but I have to think through the dimensionality issues here. But let's see. Query should be unbatched 2D or batched 3D tensor, but receiving 4D query tensor. Yeah, we are sending 4D query tensor because the X was 4D. This this guy over here had 4 dimensions and we are passing that here. Now, how can we convert this into, what if I rearrange? Let's do one thing. Let's first run with XS and XT and let's see, let's then think about why does it make sense to pass the same in. This also has become a habit for us, right? We are passing always the same input, but it doesn't make sense to pass the same input because my query is created from all the tokens. My key and value are created from temporal ones. If we do not rearrange, so if we do not rearrange, so usually this multi-head attention expects 3 dimensions, right? Batch dimension, sequence dimension, and embedding dimension. So I think this 4 dimension might still cause a problem because that's usually that's how you have, right? You have a sequence of tokens of certain embedding dimension, and those sequence of tokens are there in multiple in different batches. So usually that is what this expects, I think. So you still need a 3D dimension. Okay, let's do one thing. Let's first run this to see if it actually works or not. If it works, we can discuss further. But yeah, I'm pretty sure it works, but I just want to show you the final accuracy that I got, which you guys might want to try different hyperparameters. So I ran for 10 epochs. So here I'm not even running validation simply because the total number of images that I have per class is like around 20. So now if I split that into train and validation might have what? 4 images or 4 videos. So with 4 videos, it doesn't make any sense to define any validation accuracy. But for training, for 10 epochs, I ended up at around 80% accuracy, which is not the best. I mean, these videos are very easy. Even if we did not have any temporal attention, I'm 100% sure a vision transformer can easily identify because this is deadlift versus bench press, which are visually different looking exercises. But if it was biceps curl versus some other similar looking biceps exercise, it would have been difficult without temporal information. But here, I don't think temporal information plays a big role in classification. Um, so if anything, that extra temporal parameters are only hurting us right now. This seems to be running, I think. But now let's discuss what can we do to pass. So for key and value, why are we passing this entire XT? Why not? Query can be anything, right? Query can be for any query. You can pick from any of the input tokens as we discussed. So you have NF+1 tokens. Query can come from any of that. Key, on the other hand, if we are considering for a given spatial token, key will come from only that particular space. If we are considering temporal tokens, key will come from only that particular space. So I don't think query is wrong here. I think query part is correct. I'm just thinking, are these two correct? Should these two be something else is what I'm thinking. Same for this, same for spatial. I think query is correct because we have a bunch of tokens with spatial, I mean, query, these are sequence of spatial tokens. This is the embedding dimension. And then we just group the batch dimension and temporal dimension together. So query can be any of the tokens. So this part I think is fine. And by rearranging, we get the 3D structure, which is what Python would expect in multi-head attention. So that is also fine. So I think we need rearrange function. we are passing the right thing here. Only thing which I'm not sure is, are we passing the right thing here for key and value? And here also, are we passing the right thing? I have to think about it a little bit more. Okay, this is definitely running with very bad accuracy. If it was 50%, it would have been the worst. It would be as bad as random classification. But as I have shown you here, it is reaching 80%. And if you run for, I'm sure this is like overfitting after some point. But 10 epochs, 80% accuracy is not too bad. I have already posted a couple of assignments. I mean, one assignment in which there are multiple questions. So what I have asked you to do is, here I have divided the video into frames already. And then I'm using this class to create data set from the frames. But another option that should be available for me is inputting a video directly. And framing and all can happen here in the code itself, in Colab code. I mean, I created frames using a separate code in the first place for sure, but creating that frames can happen here in the code. So that is one task which I have added as an assignment for this week. Second task is adding multi-class classification. So currently it's a binary classification in which we have not, first of all, optimized any hyperparameter. I'm actually very curious to know if you did not use the pre-trained vision transformer, okay, and you train from scratch, but then you are not limited to the 768 dimension. You can go with smaller dimension. You can go with smaller depth. So try smaller image size, maybe 128 pixel instead of 224. Smaller image size, smaller embedding dimension. But this embedding dimension you can't change if you are loading pre-trained weights, because pre-trained weights, they are expecting a transformer of certain embedding dimension. So I really want you guys to just play with these numbers and don't load the vision transformer weights. So just comment this part out. Try smaller numbers, try smaller image size. So here we are loading 224. Where is that mentioned? Here, image size is 224. So, and actually that is mentioned here. Load a smaller image. Try multi-class, like 5 classes or something, and you can download those multi-classes from the Kaggle dataset which I showed you. Just search kinetics 400 dataset 5%. So this will give you a smaller dataset, 5% of dataset, 5% of kinetic dataset. And from this, so what I actually did was I manually downloaded this 36 gigabytes folder into my computer. And then from that, I picked 2 of the folders, like 2 of these 2 folders. Remaining folders I deleted. And then from those folders, I converted videos to frames. And then once I converted to frames, I uploaded it into Google Drive and then connected Google Drive to Google Colab for running this. So it was a bit convoluted process. Instead, what you can do is you can download it and pick any 5 folders, let's say these 5 folders. So it will become like a 5-class classification. Don't split image videos into frames. Upload the videos directly into Colab, into Drive, and then use Google Colab to split the videos into frames. Just try that. That will be a cleaner code. And this thing, I will meanwhile think about this and I will let you guys know why. I strongly think we are, if at all we are making a mistake, we are making mistake in key and value. I don't think we are making a mistake in query. So this is not wrong, I think. If at all we are making a mistake, I think these 2 are wrong. Same. If we are making a mistake, I think these 2 are wrong. Query, I think, is correct. So I'll think about why this is correct or wrong and why this is correct or wrong, and I'll let you guys know. But the exercise for this week is making the code a bit more efficient by allowing video input directly, making it possible for multi-class classification, removing the vision transformer pre-training so that you can play with the dimensionality of the model, and then changing any other hyperparameters to get, I'll be very happy if you even get 60% classification on 5-class classification on this, because this is a bit difficult model. Another thing which I had tried a bit before was I shrunk the entire spatial dimension by performing a pooling. So spatial dimension, I pooled into just 1 pixel value, so that spatial attention was not even required and only temporal attention was required. and then I applied the same things. Still, I was getting similar accuracy. So I have tried a few combinations of model variabilities to see what kind of accuracy can I get. If I train for 30 epochs, I notice that I'm getting 92% training accuracy, but I'm also pretty sure some overfitting is happening because I don't have a big enough validation data to see if actual overfitting is happening or not. But I'm almost convinced that some overfitting is happening when I'm doing 30 epochs. So you can also try few things. Okay, yeah, one more thing I forgot to mention. Have validation data also. So if you need validation data set, one thing you can do is, if it's like, let's say, uh, squats versus bench press exercise, you can download such videos from YouTube directly using some YouTube downloader or something, and use those videos as the validation data set. So you will need at least 10, 15, 20 videos downloaded for having a decent, meaningful validation percentage accuracy. If you just have two data sets in validation, doesn't mean anything to have 100% validation accuracy, right? Because two videos you had, two of them were predicted right. Doesn't make sense. So at least have around 100 videos in training total, and maybe like 30-ish videos in validation. Currently, I have around 60 plus 30, 80, sorry, 60 plus 20, around 80, 85 videos for training and none for validation because I don't have a big enough data set downloaded ready, but that can be easily fixed. So these are the things that I want you to try. And if we can initiate a discussion about whether we are implementing key and value correctly, that'll be great. You can initiate it on Discord. But thank you so much. TimeSformer is actually architecture-wise, it's simple. Idea-wise, it's simple. But when it comes to Python implementation, always there is something that is tricky. Next lecture, I am most likely planning to cover either Lava or Flamingo model. So the models that we have to now cover are Lava, Flamingo, and Stable Diffusion. And I'm also thinking of covering Dino, not necessarily V3. V3, although it's the latest model, I'm thinking V1 because we need to first understand what is Dino. Only then we can understand Dino V3. So that's the plan for the remaining lectures. So totally there will be around 5 to 7 lectures, or rather 4 to 6 lectures from now to wrap up the whole series. Some models, depending on its size and complexity, I may need 2 lectures, though that's the reason why I say 4 to 6 lectures. But that's what it is. I'm looking forward to seeing all of your submissions on assignments for those in Pro Plan. I'm looking at your submission, although I'm yet to start grading them one by one. So just do submit the assignments. So thank you so much. I will post the lecture video as soon as it's over. I have already posted the notes and code files. Just have a look at it. So thank you so much. We will meet again next Saturday. And Happy New Year. I hope everyone has a good, prosperous, healthy New Year. Thank you so much. Bye.